Okay, today is Vectors Day 2. And today we're going to talk about, well, first of all, a little bit of a review of what we did before. If I were to go at that angle right there, and I just keep going with it, how would you describe that? I mean, it's kind of going sort of that way. I mean, how could you describe it? Well, I've happened to put its start at the origin, which means you could kind of describe it in a lot of different ways, but do you get that this is kind of the key point right there? And that could be described in terms of x and y? So instead of just saying, well, okay, this ray kind of heads that way and is kind of about this long, you could be really specific. How long is it? I want you to, here, I'll count it for you. It goes 1, 2, 3, 4, 5, 6, 7 that way, and it goes up 2 this way. That is not one of those Pythagorean triples. So take a second, figure out how long it actually is. Square root of something. That's what you always do. Square root of, and then you take the two sides and you square them, and you either add them or subtract them. In this case, what do we do? Add them. So 7 squared is 2 squared is, and the 49 and the 4 makes, so that length is the square root of 53. Would you agree that the length of it is supposedly supposed to be something important and it's got a name that starts with an M? The magnitude of it. Now, as far as the direction of it is kind of that way. But if you wanted to describe it in terms of the direction of it, you could say that it's heading in such a way that it goes 7 to the right and up 2. We're going to be using that way of describing vectors eventually. Okay, but for right now, we're still just drawing little line segments. All right, so this is, I'm going to try not to say the word ray all hour, but I have a disability on this. I seem to keep on wanting to call these things rays, and they're not. They're called what? Vectors. All right, so every time, if I ever say the word ray, I want you to make an annoying buzzing noise like, eh! It's going to be like aversion therapy. You can do that with smoking too. Like every time you smoke and you catch yourself smoking, you can like take a rubber band and snap yourself. All right, so it's kind of like that. All right, so let's test it. So if I said take this ray right here, all right, very nice, good. So not a ray, it's a vector. Very good. All right, good. So now, here's my question. How could I name this thing? There's two different ways. What you just said, say it again. You can call it AB, and that means I have to put 2 points on here, A and B. And I could call it AB. Would that be different than BA? In fact, very specifically, BA and AB, when added together, equal the zero vector. As in, they're opposites of each other, right? By the way, when the zero vector has 0 magnitude, it has a magnitude 0. And it has a direction. Remember what I said about direction? We figured it out, I think, in your hour, actually. All directions. And a kid last hour said something I thought made sense on that. He said, if it's going in all directions, then every direction has an exact opposite, and they're just all going exact this way and that way, and it cancels each other out, and then it equals 0. I kind of like that way of thinking of it. It's kind of like it's going this way, but it's also going that way, and that cancels it out. And so, anyway. So it has every direction, which really means it has no direction. All right, so what's another way I could have named this thing? Yes, sir. Just A. And if you do that, just to clarify, you use a lowercase one. And then you put the little half arrow over the top. If I did do the whole arrow over the top, it would be called something else. This one is a vector. All right. So we use that little half arrow thing. All right, so yesterday I told you how to do this where I don't have to line these up nice. I can put vector C over here, and then I can say I'd like you to add vector A and vector C. Now you can tell from how I did this, I made it very simple, you know, that there's kind of 2's in both directions. See if you can add vector A and vector C and draw me the resultant. This is on your iPad, which is supposed to be in graph paper. If you haven't already got graph paper loaded up, get some graph paper up on there. Because, yeah, I don't want to just kind of generally draw these in directions. You can just do the insert page and then choose the page type. I'll pause for a second. Let me do that. Okay, I'm back with you. So we're going to be adding these. So I'm just going to drag it over and put it right here. And is that the answer? No. But it shows me where to draw the answer. The answer is called the what again? The resultant. And the resultant would be like that little black line I just drew. And that one is a ray all by itself. All right, there we go. That was actually just a test. This was a test of the emergency ray system. All right, good. So that is a vector. All right, so what happens if I instead say I want you to take A and subtract C? I'll give you a hint. We said AB and BA were exact opposites of each other. I now want you to take A, and instead this one was, you call it, the magnitude is A, I don't know how long it was. We actually figured it out. What was it? Square root of 53 plus C. I want you to do A minus C, and I'll give you a hint. You can't really subtract. But you can add its opposite. Try to figure out where that goes. I get this one out of here now, because this was when we added them. Now, oh, that's there. What's going to happen when we subtract A, vector A minus vector C? A little too curly, looks like an E. There. Did you figure out that you're going to have to go the exact opposite direction? And therefore, I can't set it that way, or that would be tail to head. It doesn't go that way. It goes like this. And so your resultant would be down here, the green one. Raise your hand if you had that right. Only a few of you did, so I'm going to give you another one like it. All right, what happened there? C was normally this way, but we had to reverse it, go the exact opposite direction, but the same length, and go down there. All right, so would you please draw me a little vector that I'm going to call RS. And I would like this little tiny vector over here called MN, like Minnesota. And I would like you to tell me what it would look like to take RS and subtract MN. And again, I like to think of this as you really can't subtract, but you can add the opposite. You think of it however you want, as long as you can get the right answer. I'll pause, retry that. All right. So I have made this MN the opposite. And so think about this for a second. You get, that would be like saying, take RS and add what? Not negative. Add what? NM. Do you get how this is really NM if I put the arrow on the left end of it there, or the top end? So you're really adding, if you switch it around, instead of subtracting mn, you're adding nm. All right, and then when it's all done, you should have had a resultant. I'll make it with this super sharp black line right there. There we go. There's your resultant. Raise your hand if you had that one right. Okay, good. What if I said 2rs plus mn? What would your gut feeling? What's your best guess if I say 2rs? What do you think that means? It's got a scalar involved with it. What part of it is the scalar? If I say it doubles the magnitude, and the magnitude is the scalar part. So when I say 2rs, I'm doubling rs's length, but not messing with its direction. So do you get that would be 2rs? Okay, and then if I'm going to add mn, just go like that. Boom. And the resultant will be that then. That make sense? All right. Quick reminder, if you've got a triangle that's not a right triangle, can you still find the lengths of its sides? Is there a relationship between them? Yes, but you need to know one angle to make it all work. If you know it, write the law of cosines on your iPad right now. Starts with a squared plus b squared, and it all ends with c squared. But there's something in between that you need to know. Again, the thing that's special is it doesn't need a right triangle to work. All right, you should have said a squared plus b squared, and then the factor I didn't say equals c squared, and what is that factor I didn't say? Minus 2ab sine of big C. Cosine, thank you. Cosine. All right. That's the factor that changes it so that you can use it. Actually, it still works on right triangles. It just happens that that part turns into what? 0. So if we were really needed you to memorize this, we would have just never told you a squared plus b squared equals c squared was a thing. We would have just told you to do this, and then it would just happen that this would turn into a 0 lots of times. All right. Anyway, that could be used on this problem. If I told you that this angle was, let's say 100 degrees, that angle's 100 right there, and this side right here is, well, actually, I can figure that one out. It's 1, 2, 3, 4, 5, 6, 7 for the base, 1 for the height. So that's square root of 50. Good. I got an angle of 100 and a side of square root of 50. And let's make one more side here. I bet I can do that one fairly easily. What's that side? Square root of 2. Good. I could figure out the other sides and the other angles using law of cosines. All right, what's another law? Law of sines. It's actually easier to use, and it works really well when what? And an angle. And what's special about the two sides in the angle? This is the important part. One of them has to be across from, like, you have to know an angle and the side across from that. Do I in this case? Yeah, I said this is 100, and I said this was square root of 50. So yeah, I know an angle and a side across from it, so I could use the law of sines. What's that? Sine big A over little a, because the angles are big, or the capital letters, and the side lengths are the little letters. Okay, equals what? Equals sine C over little c. And could you flip that all over? Yeah, it doesn't matter which way, which one's on top. You could say the little a on top over sine A, little b on top over sine big B. All right, good. Just want to remind you about those because I'm just starting a little gentle review process. Throw a few things like that in every now and then. That way, when we hit the review, it isn't going to be like, oh my gosh, so much to know. All right, so I taught you about adding the opposite. I taught you about doubling. That's adding a scalar, okay? So what happens if I don't tell you what the picture looks like at all? No, actually, wait, one different way to say it. What if I say, here's a picture. I'll do the no picture one in a minute here. What if I say vector AB plus vector BC? What could you say for sure the answer is? AC. All right. Then, when I said AB, I gave you direction. And vector BC gave you direction. All right, so another way to say that would be, this is different now. That vector, which is called what? CA, is equal to what? It's like I gave you the question, or no, the answer, and then you got to give me the question. What is, very good, you put it in the form of a question, that's good. What is what? What do you think it is? CB plus BA. Now I'll see if you're right. CB plus BA. Yes. If any of those letters had been reversed, it would not have been right. And I couldn't have said BC. Well, actually, let me think about this. Could I have said BC plus AB? Would that have worked? BC, which is this guy, plus AB, which is that guy. Remember, we got to do them in just the right order. BC plus AB. Yeah, that's way over here. That's nowhere near the same. Okay. What else could you have said that would have brought you to the same place? There's another right answer. This was not. It's another right answer. Mr. P? Oh, no, Mr. P. P, not B. Sorry.
Negative AB minus BC.
Check. Negative AB minus what? BC. I think you're right. I'm going to find out. When you say negative a vector, you basically just take and turn it around, make it the opposite, right? All right, good. That works. There's one more way. AB plus BC is the theory. AB plus BC is a vector that's going the opposite way that I want. Do you get? It's a vector AB plus BC gives me that vector, which is going the exact opposite way of what I wanted. So you're really close. This is just factoring. There you go. I know. It's just factoring the other one. It's kind of cheating. But. Okay. So, how about this? What if I don't give you a picture, but I say AB plus BC plus CM? How could you possibly know what that is? I know what it is. Think about it. What is it? What AM? Vector AM. Now, just because I don't know what it looks like doesn't mean I don't know that the answer is AM. See, I could draw it if it wanted. Here's AB. I can totally make things up. I can be any direction I want to right now. BC, I want to make it that way. And then CM, predict which direction I'm going to go. Wrong. I'm going left. All right. And then the final answer is A to M, wherever they may lie. There's the resultant. Okay? All right, so then I'm going to mess with your brain a little bit. What's AB minus BC plus CM? Minus CM. All right, how about this? Did we establish before that AB minus BC would be the same thing as AB plus CB? You with me? All right. Plus what? C. Now, unless I know what directions and what magnitudes they are, it's going to be really impossible to know what this all adds up to. But I can tell you what its magnitude would be. Magnitude of. All right, mess with your brain a little bit more. What's AB plus BC plus CA? It's a good question. AA, no, we don't say it that way. It's the zero vector, which has how much magnitude? 0, and how much direction? Or which direction? All directions. Okay, good. So what do you mean? Well, because AB can go anywhere, and then BC can go anywhere, and then CA, though, has to go back here to the starting spot, and therefore it's got to be back in the original spot, and therefore 0 magnitude. And direction, well, we really don't have a direction, so we say all directions. Yes? You write 0 vector. Okay. So, how about we make a shortcut for that 0 vector? Cool? All right. So, if you were to be asked, I want to change this to AC. No, I'm wrong. Don't do that. Okay, let me think now. Okay, I'm just going to go one more. Plus AM. Get how this one got me all the way back to where it was in the first place, and then it's just the new vector. So it's like all of this turned into what? 0. 0 plus AM is just AM. Or another way to think of it is, once I got there to there to there and back to here, now I went to M wherever it is. So this part didn't even matter. That's the resultant. All right. So, last topic that I need to cover with you. Actually, let's look at the homework together. So everybody grab your homework. Look for day 2 of the homework. Assignment day 2. High 30s. 34, it sounds like. All right.
35, 34.
35. Okay, here we are. I'm going to cut out a couple, but these are all important for you to know how to do. All right, this one's a little bit of a mind bender. It does say it's going to take a few minutes to do this one. It's not just an instant, oh, add this vector and add that vector. Okay, it says OA is little a. That's little a. And I wish they had little vector symbols over them. Okay, so the little a is between O and A. And does it matter which direction it goes? Yes, it does. So I draw over it in one color, like blue or something. Because little a is going in that direction from O to A. Okay, next. OB is little b. That's little b. And OC is little c. Now that you know that, what's AC? Would you agree? AC. No. Oh, okay. I agree that AC, which is right here, could be made up of like AB plus BC. Would you agree that this one I just drew here? Oh, no. Hold on. This one I just drew here could be AB plus BC. Does that make sense to you? But you can't use those. You can only use A, B, and C. Unless you could figure out some way to make AB with little a, little b, or little c, and BC with little a, little b, and little c. Or maybe I just have to like add opposites together. Maybe I have to put B with opposite of A or something like that. Remember, you can do opposites of. I want to do opposite of A. We can do that. I'm going to make it a dotted line here. I'm going to change colors to purple and do a purple dotted line. This is A opposite. And then you can grab it and move it because you got your little tool. And then go like, could I do that? Nope, that one didn't work. Unless what I get here, the resultant would be like this. If I moved it to another spot and it was like lined up with something else. All right, I don't want to tell you too much. You have to figure that out. It's not impossible by any means. And worst comes to worst, you have a key. You can look it up if you shouldn't just instantly go look at the key. You're making yourself weak if you do that. All right, this next part, number 2, that's the easy stuff. That's the stuff where we were just adding vectors, except now we're subtracting vectors. Or we're doubling this vector, which means just make it twice as long as it was, same direction. And then subtracting that one, except 3 times as big as it was. Remember, adding A and B was really easy. There. And then the resultant was like here. But subtracting them is very similar. Instead of adding it, you just go the opposite direction. And the resultant will be up here. Okay. Next topic. Oh, and you got some room to draw these down here. You know, so if you're going to draw your answers out, I think it comes out to that or whatever. Resultant. Okay. I'm not saying that's answered one. Then, simplify. This is as simple. This is super simple. You do not have to draw a picture of these. Can you tell if this is vector wx, vector xy, and vector yw? What's the answer? What did it start with? W. What did it end with? What does that mean? It's a 0 vector. Okay. Part B. Instead of subtracting SR, you never want to subtract in these. Add RS. And then add QR? Maybe you should make a little picture to try to figure out. Now, you won't know exactly where they are because you can make up anything you want for their pictures. But all right. This just means 6 times as big as BC was. It's a scale factor in front. Remember, scalar is just like a number that like doubles something? As opposed to vector. Vector has magnitude and direction. That's the 6, that's just a scalar. All right, on this one, I want to remind you in your little prove that thing, it's very simple if you remember, if you know one thing. You're going to somehow regroup that so that you end up with opposites. Opposites are like this. Do you get that BA would exactly cancel AB? What if you were to add BA and AB together? You get the 0 vector. They would cancel each other out. They would equal 0 for sure. That's a definition. That plus that has to always equal 0. So, show me why this one equals 0. Again, I suggested you group those somehow. Rearrange those somehow. All right. And, oh, and you can skip this part, part B. Moving on to this. Consider the cuboid, blah, blah, blah. It's just the same exact thing except in 3D. Get used to 3D. We're at the beginning here of vectors. You're not going to be doing too much to the super easy stuff on your tests. Got to be able to handle the super easy stuff to be able to get to the medium stuff that'll be on the test. This will be more like medium level vector stuff. Remember, this is all vectors that go in that direction. So BC, it's like it has a little vector thingy over the top of each of these. All right. And this just is saying that the magnitude of A is 2. That means that has a length of 2 right there. Get how you could like find the volume of the box pretty easy if I give you enough magnitudes? Okay, or just the length of other segments in that. That's really a very easy question. So do number 8 also. And that is it. You do not need to do number 15. It's a big beast of a problem, like that big gigantic aircraft carrier of a problem. Yeah. All right. So, yeah, that would take anybody who's really, really good at math 4 minutes to do. Because there's people that are just learning this stuff. That would take you much more than 4 minutes. Okay, that's all I have for you for today.